So we've seen the construction or working of a single phase transformer, right? So now in this topic we are going to see what is the EMF equation of a single phase transformer. So in a single phase transformer we have two main components, right? See, one is the supply which you are providing to the primary side of coil, and then the magnetic field which is generated due to the power supply, right? And the third parameter which plays a major factor in the EMF is the number of turns of coil, right? So using these variables we are going to find out the EMF produced in a transformer, right? So the EMF can be given by N into d phi by dt. So N here represents the number of turns of a coil, and d phi by dt represents the change in magnetic field. So since in ideal condition, if the number of turns is the same in both primary and secondary coils, so what is the remaining factor which is going to induce the EMF? So the EMF will vary only based upon the magnetic flux, right? So in this condition, if the number of turns is same, you can say that the voltage induced in the primary will be the same as the voltage induced in the secondary, since the same magnetic flux is linking both the coils, right? And also the total voltage induced is directly proportional to the number of turns in the coil. So since we are providing an AC power supply, the magnetic flux varies sinusoidally, right? So we can represent the magnetic flux as phi is equal to ϕmax sine omega t. Now substitute this equation in the EMF equation of a transformer. So what will happen? So E is equal to N into d phi by dt. So we have to differentiate the ϕmax sine omega t, and finally you get E is equal to N into omega into ϕmax into cos omega t phi. So this is the EMF equation of a single phase transformer, right? So if you are calculating the EMF for the primary winding, it is called as the NP, right? Right? So NP represents the number of turns in the primary coil, and if you are calculating for that, it is called as EP, which is EMF of primary, and similarly we calculate for secondary separately, right? Now we have two conditions, right? So one condition, the number of turns in primary can be greater than the number of turns in the secondary. So in primary we have higher number of turns in a coil, and in secondary it is comparatively lower than the primary. So what will happen? Your EMF is directly proportional to number of turns of a coil, right? So if N1 is greater, then EMF generated in the primary side will be greater. So primary EMF is greater than secondary EMF. So this condition is called as a step down transformer. So what will happen? If you are providing a high voltage to the primary of a transformer, the secondary you will be getting a low voltage. So that is called as a step down transformer, right? And the second condition is the number of turns in the secondary is greater than number of turns in the primary coil, right? So what will happen? EMF induced in the secondary coil will be greater than the EMF induced in the primary coil. So this is the opposite of the first condition. So here what will happen? The secondary output will be higher than the primary voltage, right? So this is called as a step up transformer. Converts a low voltage into high voltage, right? So this is the basic two conditions for a transformer: step up and step down, right? So in the next slide we will see about the different types of transformer and their applications.